A wave is a wiggle in space and time. Not part of your notes, but this is the definition of a wave. Most importantly, a wave carries energy. We just did a unit on energy, and a wave carries energy. It is an energy type. And we are going to talk about two of those energy types in this unit, which would be sound waves. Sound carries energy, and so does light. Light waves carry energy. Okay, some waves require a medium. When I talk about a medium, it needs something to travel through. So when you did your Slinky lab, the Slinky is your medium. If you're talking about sound waves, air is your medium, or water, but it has to have something to travel through. There are certain waves that do not, and we're going to talk about that in a little bit. Okay, we just talked about density matters, right? For high density objects, that makes the speed of the wave slower. There are certain exceptions to this, and we're going to talk about that when we get to that unit, but density does affect a wave, how it travels, and its characteristics. And as we stated, something that is denser carries the wave more efficiently. This one says it'll carry the wave more quickly. And this is specifically referring to sound waves. When we had high density Slinky, the high density actually made it move slower, as we stated, due to inertia. But when we're talking about sound waves, density is important. All right. Let me know if I'm moving too fast. Okay, there are two kinds of waves. One would be electromagnetic. So that's going to be in the top part of that box there. The thing about electromagnetic waves is we can't see them. So you can think of them as X-ray waves, UV waves, radio waves, microwaves. They do not need a medium to go through. So this is unique about electromagnetic waves, is they can travel through space and they can travel through a vacuum. And then some examples, as I stated, are light, radio, X-rays, etc. Light waves we can't see, but light is a wave that can go through space, unlike sound waves. Okay. Anyone need me to keep this slide up? Let's go on to the mechanical waves. We talked about mechanical energy. These are mechanical waves. These we can see, and if we can't see them, we can at least see the effects of them. So a sound wave would be a mechanical wave. You can't necessarily see sound waves, but have you felt the bass of sound or the vibration of sound? That's the effect of this mechanical wave. And they absolutely need a medium to go through. They cannot travel through space. And some examples would be the water waves, your sound waves, and a Slinky. So if you've ever watched a movie where maybe a rocket or a space shuttle is blowing up in outer space, you'll definitely be able to see it because we can see light in space, electromagnetic waves, but you absolutely would not be able to hear it. So for movies that get that physics concept wrong, you should not be able to hear explosions in space. Common error that happens. All right, question.
Wait, so like you can't hear like any sound, like you couldn't talk to someone in space, but you can hear sound if there was like a space shuttle.
So if you're in a space shuttle, then you've got air. Air is a medium.
Oh.
And so you would be able to talk to each other if you were in the space shuttle. But if you were outside of the space shuttle trying to communicate in outer space, you would probably have microphones or something within your spacesuit because sound waves cannot travel through air. Okay, this was just a quick understanding. Can you tell me which of these is a medium? We want to think about what that definition is and which one is not. So on your paper of the examples, just write which one is not a medium. Actually, I already gave away this answer. Which one is not a medium? Space. I already told you. Or a vacuum. And we can create vacuums here on Earth and actually show that it eliminates sound. I'll try to pull that video up. But yeah, you can have sound travel through cement, water, metal is a really, really good conductor of sound, rock, wood. All of those things actually allow sound to travel faster because, like I said, unlike our slinky, high density medium allows sound to travel faster than on air. Okay, let's go through this quickly. Okay, a medium is made of lots of individual particles. So you're going to think about it as, for example, air particles in the air. It vibrates in response to a wave, but it does not move. Question.
So you're saying higher density faster?
In terms of sound waves is the exception to this slinky scenario. Most of the time, if you have a wave traveling, for example, a water wave, high density is going to be slower.
Okay.
But when we're talking about sound waves, high density makes it faster. And one thing that a lot of students don't understand is that waves do not actually transfer matter. It only creates a vibration. So if you think about your slinky that you're playing around with, each coil vibrated, but did the coils actually move to the end of your slinky? Was there any physical motion of that coil moving? No, it just vibrated, and that vibration made the coils in front of it vibrate, and then it created a wave. But it didn't actually move any matter. It just created a vibration, which transferred energy. So we're going to go through some examples of this in a second. Any questions, or does anyone need me to leave this up? Okay, a pulse is what you created today. One pulse is a single disturbance in a medium rather than continuous. You could have kept creating waves, and that's another type of wave. But to really see the speed, you have to create one pulse. So this is the definition of pulse. Again, a lot of definitions. One disturbance in a medium rather than a continuous repeating wave. Okay, and then for your chart, what you're going to do is add all waves carry energy. We just completed our energy unit. You're going to categorize the two types of waves for electromagnetic and mechanical. You don't have to put these two because you already took notes on that. Just write electromagnetic and mechanical. And then within mechanical, you've got your transverse, where you have the perpendicular motion of the wave. You've got longitudinal, where the wave motion is parallel to the wave vibration. And then a surface wave I'm going to talk about later. That's the waves you get when you are in the ocean. They actually go in circular motion versus a transverse has perpendicular motion. The wave is moving perpendicular to the direction it travels. Longitudinal is parallel. And then surface goes like this, around in a circle. It's a combination of longitudinal and transverse, actually. Okay, anyone need this slide back up? Okay, definitions. A transverse wave are waves that vibrate perpendicular to the direction of motion, as I stated. You've got the particles moving up and down, but the wave itself is moving left and right. What you want to notice is that these particles are not moving left and right with the wave itself. It just creates an up and down motion.